Hello friends. Hello friends. In continuation with the last lecture, today we are going to talk about the another topic uh, from this subject is nothing but the current density. We are much aware of the current density that is which can be calculated from the Ohm's law as well. That is J is equal to O sigma into E. But let's try to find out the current density for the semiconducting material. We know that we have the knowledge about the carrier concentrations in the solids, and is very necessary for the calculating the current flow in any kind of the material. Is also applicable for the semiconductor as well, and this current flow is possible only when there will be the application of the electric field or else the magnetic field as well. Okay, so we'll be looking only application of the electric field and how its conductivity can be calculated. So now the charge carriers in the solids are in the obviously the are in the constant of motion, are in the constant motion, even at the thermal equilibrium, means even at the room temperature also we can consider, because room temperature temp is around 297 Kelvin. So this much thermal temperature is also sufficient to vibrate these electrons or the charge carriers at that temperature. So they will be having the in a constant thermal motion, and because of that motion, obviously these electrons individually will be visualized as a random scattering from the lattice vibrations, even impurities, and other electrons and also the defects as well. So this scattering is very random, and there is a no net motion of the group of the electrons per cc over the any period of the time. So this is actually not an individual electron, or of course. So now when we are talking about the total probability, we must talk in terms of its probability of the electron returning, or else sometimes what we can say, the electron is starting from one place, and it just if suppose the electron is starting from this place, and what is the probability of the just scattering with the other electrons and coming back to its again the original position, or let's say its initial position. It's a very rare possibility of returning back. If suppose there are a large number of the electrons are considered, and there will be the preferred direction of the motion, obviously there will be some preferred direction of the motion of these electrons, and no net current will be flowing in that particular material. So now, if suppose there is no net current flow is flowing in a particular direction, if suppose we try to apply the electric field, so in this direction, if we just try to apply the electric field, suppose I consider the positive x direction, obviously the electrons will be moving in the opposite direction. Okay, so in this direction. Okay, so the field is applied along this direction. Now, let us this consider the group of the electrons at time t is equal to 0, and we have defined the n of t as a number of electrons that have not undergone a collision by a certain time t. So these are the number of the electrons which have undergone any kind of the so now uh, what is the this rate of decrease n of t at any time t, which is proportional to the number of the electrons remained unscattered at time t. So this rate of decrease in n of t means the what is the how means the number of the electrons which are not scattered, okay, are not undergone any kind of the collision. They are going to get decrease over the period of the time, and that is proportional to the number of electrons remained unscattered after a certain time t. So this is given by the equation dn of t by dt is equal to minus, or it's proportional to, actually it is proportional to n of t, and if we just minus n of t, because this negative sign indicates the decrease of in n of t over a period of the time. And if we just try to remove the proportionality constant, there will be the some proportional sign, then we can just replace that proportional sign with the equality sign, and there will be the some constant, proportionality constant, and that proportionality constant can be calculated as 1 over t0. Okay, so 1 over t0 is the proportionality constant and can be easily calculated. We know how to solve this differential equation. So the solution of this differential equation is a exponential function. Okay, solution of this equation is a exponential function, and which is given as n of t is equal to n0 e raised to minus t by t0. Here t0 represents the mean time between the scattering events, and also it is also called as the mean free time. Mean time in the sense that there is a time required for the electron to have the successive scattering from the one object to the other one. So that timing is called as the mean free time. Now the probability that the any electron has a collision in the interval dt is a dt, because t0 is the mean time, is average over the all the collisions it has happened. So the if suppose we consider the some small time dt, then the probability that the electron will have the collision in that small interval is nothing but the dt by total time it would take, or mean free time. Thus, this differential change in the momentum of the electron along the x direction due to the collision in time dt is dt by t0. So dpx, so it's a change in its momentum. Okay, or to just before we go for this dpx is equal to minus px dt by t0, let's try to understand that the how the steady state has been considered over here. Now the net acceleration of the electron after the application of the electric field along the forward direction is just balanced by the steady state by the deceleration of this collision process. So when we apply the electric field in the forward direction, obviously there will be the deceleration of the electrons in the backward direction. So this will be what we can say, it will be the balanced condition. So thus, while the steady state electric field does produce the net momentum, that net momentum along the along the opposite direction. What you can say, if suppose the applied electric field is in the forward direction, obviously the electron will have the deceleration or the momentum along this negative direction. Okay, this is the negative x direction, so it will decelerate along this direction. So its momentum is given by the p along the minus x direction. Okay, so this is what the we are having along this negative direction. So this acceleration or net rate of change of the momentum when the collisions are included must be the zero in case of the steady state current flow, because electric field is applied along this forward direction and the deceleration along the in the backward direction. So this will result us in to the steady state condition. Okay, so the dpx, so this what we can say, differential change in the momentum of the electron along the x direction is given by dpx is equal to minus px dt by t0. So the rate of change of px due to the decelerating effect, which is decelerating effect of the collisions, is given by dpx by dt is equal to, because of the collision, is minus px by t0, and the rate of the px due to the accelerating effect result from the application of the electric field along the x direction, and which is given as the dpx by dt due to the application of the electric field is equal to minus n q ex. Now the sum of this acceleration and the deceleration must be the zero for the steady state curve. We have already discussed about the steady state, how it is occurred in this Okay, so this, if we just try to take the sum of this above the two equations which we have seen, we will get is nothing but the minus px by t0 minus n q ex is equal to, you're just summing them together. So the average sum per electron is given as average momentum px is equal to px by n, because this is the total number of the electrons we have under the consideration, is equal to minus n. I just try to substitute the value of this uh, average px into the above equation. From this we will get the minus q t0 ex, where the angular brackets, okay, this bracket indicate an average over the entire group of the electron. So uh, this equation represents that the electrons have on the average of the constant net velocity along in the negative x direction. So this indicates the negation over there. So which is given by, okay, which is given by the average px is equal to average px by mn star is equal, n stands for the negative charges, is equal to my number of the electrons are present over here, is equal to minus q t0 by mn star ex. Okay, actually this individual electrons move in many direction by the uh, thermal motion during the given period, but this equation tells us that the net drift of an average electron in response to the electric field. So this is net drift because of this application of the electric field. So the drift speed is usually much smaller than the random speed due to the thermal velocity of the or thermal motion of the electrons. So the current density resulting from the net drift is just the number of the electrons crossing the per unit time multiplied by the charge on that electron one. Okay, so the actually the individual electrons move in many direction by the thermal motion, and during this given period of the time. But the above equation tells us that the net drift of an average electron in response to the electric field is present over there, which is given by so this is nothing but the outcome of this is nothing but the current density, and current density which is resulting from the net drift, and which is net drift is given by Jx is equal to minus Qn Vx, or expectation value of the Vx. Using the value of the average value of the Vx, or the expectation value of the Vx, we have Jx is equal to plus Nq square T0 Mn star Ex. Okay. Then what okay, so thus the will get the current density which is proportional to the electric field. From this equation what we can get, the nq square t0 and mn star all are constant, and so obviously the jx will be the proportional to the uh, ex. So jx is equal, so from the what we can say, this quantity is considered as sigma, this quantity is considered as a sigma, and which is nothing, this equation is nothing but the Ohm's law in the vector form. So Jx is equal to sigma Ax, where sigma is equal to nq square t0 by mn star. Mn star is nothing but the effective mass of an electron. Now the conductivity is sigma, which is measured in the per ohm meter, and it can be written as sigma is equal to n q mu n, here mu n is equal to q t0 by mn. So there is a one more quantity which is introduced over here, is the mu n. Okay, so mu n is nothing but the mobility of an negative charges. Mobility of the negative charges is equal to q t0 by mn star, and is called as the electron mobility. So mobility can be given or expressed as the average particle drift velocity per unit electric field. So this is the standard definition of the mobility, that is nothing but the average speed or average particle drift velocity per unit electric field is nothing but the mobility. So if we just try to compare the equations for the expectation of the Vx and the mu n, A is we can get it mu n is equal to drift velocity per unit electric field or the applied electric field. So the current density can be written in terms of the mobility as nothing but the Jx is equal to q and mu n Ex. So now in case of the semiconductors, there are both kind of the charge carriers are present in the material. Okay, so in case of the semiconductor, the electrons as well as the holes participate in the current conduction. Then the current density, obviously similar kind of the expression we can get it for the positive carriers as well, or for the holes as well. So if we just try to repeat the whole process, then what we can say, Jx is equal to q and mu n is equal Ex is the one of the equations we have solved. So Jx is equal to this what equation we have, this is nothing but the n mu n, and Ex was the equation which is for the electrons, okay, or the negative charge carriers. Similarly, if we just follow the if we just try to solve the equation for the holes, then we will be getting the another kind of the equation, that is nothing but the Jx is equal to q, then the p is the number of the holes present here, or the crossing per unit through the cross sectional area A per unit time, into mu p, which is nothing but the whole mobility, and the applied electric field remains the same. So here the what, instead of the having the electric field in the forward direction, obviously the holes also drift in the forward direction only. So holes will be drifted in the forward direction. So obviously they will be having the similar kind of the direction. So here it can be utilized. So here we can have the Jx is equal to q and mu and plus p mu p into Ex, and this sigma is here, this is nothing but the electric conductivity. And in case of the semiconductor, electric conductivity is a composition of the both the components, that is uh, current conduction because of the negative charges, as well as the current contribution is coming from the holes as well. This is all about the current density in case of the semiconductors. Thank you.